Hello, I'll be discussing a problem from March lunchtime 2016. The problem is two closest. As you can see, there are 36 people solved this during the contest. So in this problem, the statement is very short. We are given n nodes and m edges, a graph, a weighted graph, and some of the nodes are called special nodes. Our task is to find the shortest possible distance between any two different special nodes. So that's it. Let's look at the constraints. So as this is a lunchtime problem, there are multiple subtasks. I'll be discussing each of the subtasks one by one. So for the easiest subtask, you can see that the number of nodes is pretty small. So since the number of nodes is only 300, we can actually find out all pair shortest path here using an algorithm like Floyd-Warshall. So in 300 cube time complexity, we can actually find out the all pair shortest paths, and from there we can find out the best pair of special nodes which has the minimum distance, right? So that was pretty straightforward. For the second subtask, the number of nodes has increased to 10 to the power 5. So of course we cannot run a Floyd-Warshall here because it is going to get time limit exceeded, but here we can see that the number of special nodes has decreased. It can be only as much as 10. So what we can do is we can run a Dijkstra considering one of the special node as the source. So we'll be doing this for each of the special nodes. So at most we will be running k Dijkstras, so basically 10 Dijkstras in the worst case, and after each Dijkstra we will see the shortest distance to the other special nodes from this source special node. So after running the 10 Dijkstras, we will actually get the shortest path from shortest path between each pair of special nodes, right? Then we can find out the minimum distance from there. The subtask 3 is where things get interesting. For the previous two subtasks, they were basically implementation of classical algorithms, but in the subtask 3 you can see that the number of nodes is still 10 to the power 5, but the number of special nodes can be as much as 10 to the power 4. So we cannot use any of the algorithms or solutions we proposed in the previous two subtasks. So for the subtask 3, we are going to discuss two different approaches. The first approach is a probabilistic one. So let me get to this. Let's just say that we have k special nodes, right? Okay. We will take two different sets. This is the set we are calling source, and this is the set that we are calling destination, dest. So initially both of them are empty. What we are going to do is we are going to split the k special nodes into two sets. So we are going to split evenly, so k by 2 nodes goes here, and k by the rest of the k by 2 nodes goes to the destination set, and we are picking these k by 2 nodes to be in the source set randomly. So these k by 2 nodes, they do not have any particular characteristics. We are just picking randomly k by 2 nodes, the half of the nodes, to be in the source set. Now we will run a multiple source Dijkstra, a single Dijkstra, but there will be multiple sources. Okay, and the sources will be actually will be coming from the source set. So we will be running a multiple source multiple destination Dijkstra where the sources are the k by 2 nodes in the source set and the destinations are the k by 2 nodes in the destination set. Let's just say we have run our Dijkstra, and after running the Dijkstra we find out that there is a node v in the set destination whose distance is 15. What does this mean? We are finding out that distance of v is equal to 15. This basically means that there is a node u in the source set from which we can reach v with 15 cost. Now let's assume that the V has among all the k by 2 nodes in the destination set, V has the shortest distance or the minimum distance. So the 15 is the minimum distance. So what this means is that for all possible pairs of nodes where one pair is coming from the source set and another one node of the pair is coming from the source set and another node of the source is coming from the destination set. For all possible pairs like this, it is true that none of the pair has a shorter distance than 15. Each of the pair has a distance equal or greater than 15, right? Why is this? Because we are running each of the source nodes. We are keeping each of the nodes of the source set as the source of our Dijkstra, and we are finding out the minimum distance for all of the nodes in the destination set. So we can say that maybe 15 is our answer. So this is our answer, we can say that. But will it be correct? Let's look through it in detail. So for example, we assume that there is a particular pair of nodes A, B. This pair of node is actually the best pair of among all possible pairs. Why? Because they have the shortest possible distance. So we want the distance between A and B because that is our answer. So what if A was in the source set and B was in the destination set? It can happen, right? So in that case, we will actually get the intended answer, the minimum answer, right? Even if A was not here, but maybe B was here and A was here. A was in the destination set, but B was in the source set. Even then, we'll get our required answer. But what if both A and B were in the destination set? In that case, we're definitely not going to get our required answer because both of A and B are in the destination set. So we will get a wrong answer in this case. So now the question is, what is the probability that we'll get a wrong answer? What is the probability that A and B will be in the same set? So let's see. What is the probability of A being in the source set? The probability should be half because we are making an even split. So A being in the source set, the probability definitely is half. Similarly, what is the probability of B being in the source set? That's also half. And these are independent probabilities. So we actually multiply them and we get the probability 1 by 4. Since the probability of A being in the set source doesn't depend on the probability of B being in the set source, right? So the 1 by 4 is the probability of both of them being in the source set. Similarly, 1 by 4 is also the probability of both of them being in the destination set. So what we can say that is that half is the probability of both of them being in the same set, right? So whenever both of the nodes in the best pair, which is A and B here, are in the same set, we get a wrong answer, right? So we do not want this to happen. So there's a 50% chance that we'll get a wrong answer, which is of course not good enough. But what if we can improve our chances? What if we didn't run one Dijkstra or one iteration of this algorithm? We ran 2 iterations of this algorithm. So let's see what is the probability that both of the nodes in the best pair are in the same set in the second iteration. Since nothing has changed, it must be 1 by 2 as it was calculated for the first iteration. So in the second iteration, both of them being in the same set, the probability is still half. Now the most important question is this: what is the probability of getting a wrong answer, making a wrong split in both of the first and the second iteration? A wrong split means a split where both of the best nodes goes to the same set. So the probability of making a wrong split in both of the first two iterations is half into half, so which is 1/4. So you can see that we can increase our chances of getting the correct answer by increasing our iterations. So instead of doing 2 iterations, what if we did 20 iterations? In that case, what will be the probability that in each of these 20 iterations we made a wrong split? A and B were always in the same set for each of these 20 iterations. The probability will be half to the power 20. This is because each of the iteration is independent of anything happened that in the past. So these are independent probabilities and they get multiplied. So this is actually a very small value, which is something like this, and we can, for practical purposes, we can actually consider this to be almost 0. Think what this means actually. Basically, we just want at least one of our iterations to have the correct split. Even if we make a wrong split in the 19 iterations, but there is only one iteration where we have done the correct split. And please remember that the source set or the splits are random every single time. So the nodes in the first split, the nodes in the source set after the first split is not the same as the nodes in the source set in the second split. So they are completely random. So for this reason, we just need one of those iterations to be correct, need to have a correct split. So the probability of that happening, that none of the iterations have the correct split, is 1/10 to the power 6. So it basically means that if we are submitting this problem 10 to the power 6 times, we can expect that one of them would get a wrong answer and all the rest of the submissions would get a correct answer. So it's a very good probability and we should be satisfied with ourselves. So finally, if we want to look at the complexity of the solution, the complexity is basically order of t into m into log n, where t is the number of iterations, m is the number of edges, and n is the number of nodes. So this is the complexity of Dijkstra, and we are running Dijkstra for each iteration, so it's up to us. We can decide the value of t. So we can maybe consider t to be equal to 20 because that's a good enough value. So this was our first approach for this particular problem. Now we'll be discussing about a deterministic solution. So let's start from square one. Previously we discussed about a probabilistic solution. Now we want to get a foolproof deterministic solution. So what we have in hand is that we have a graph, a weighted graph. The edges have positive weight, and we need to find the best possible spatial pair in the graph, which is the minimum distance, right? So let's say that we actually color the nodes in the graph. So how do we color the nodes in the graph? Let's say that the spatial nodes has a color. So let's say 5 is a spatial node. Okay. So color of 5 will be definitely 5. Now 5 will try to color all other nodes, all other non-spatial nodes with its own color, which is 5, and it will be able to color a node only if that node has the closest distance or the shortest distance from 5 among all possible special nodes. So let's just say something like this. Let's say that 5 has the color blue. Okay, so there is an adjacent node to 5, which is maybe say the node 2, and the distance, the edge, maybe 2 distance, and there is the node 3, the edge has a weight 1, and there is a node maybe 10, that's a 10, and it has a weight of 4. Okay, now we'll be changing the colors. Why? You will see in a short while. Let's say here is the node 7. 7 has the color purple, so it's colored with the purple node. And now 7 has an adjacent node 8, which is also colored with purple because it's the closest to 7, so maybe the distance is 1. Okay, so we can see that from the two nodes 2, 3 and 10 are colored with blue because 5 is closer to them, but the nodes 9, 8 and 7 are colored with purple because 7 is closer to them and 7 has the color purple. Okay, so this is the situation we want to create, and we can actually create this in a very straightforward way. We can run a single Dijkstra, only one Dijkstra, where all of the special nodes will be the sources. Okay, so all of the special nodes are the sources, and we can actually keep track of which special node is giving the shortest distance for a particular node. It's kind of like keeping track of who is the parent of a particular node while computing the shortest path, right? So we can actually compute that with a modification in the Dijkstra algorithm. But what do we actually gain from doing this? Let's just say that in our particular example, 5 and 7 are the best pair. Okay, so 5 and 7 are the best pair. So 5 is coloring with blue and 7 is coloring with purple. Now if we iterate over the edges, we look at this edge. Okay, this edge has 2 endpoints, and these 2 endpoints are blue. Similarly, this edge has 2 endpoints, it is blue. This edge has 2 endpoints and these are purple. But if we look at this edge, it has 2 endpoints and the endpoints do not have the same color. It's a special edge, right? The edge with the cost 100. So this edge has 2 endpoints, one of is blue and one of the endpoint is purple. Now we can think of it like this. The distance, shortest path from 5 to 7 can be decomposed in 3 components. One component is this part, one component is this part, and the other component is the single edge that has different color on the endpoints. So so we can actually resume from here. So what I'm trying to say is, maybe we can find our edge UV where U has a different color and a V has a different color. So now we can say that the path from U's color, the node that has U's color, the special node which has colored U, to the special node that has colored V can be decomposed in this way. Distance of U plus edge weight of UV plus distance of V. So in our example, 10 will be the node U and 9 will be the node V. So we calculate this value, right? For all edges which has different colored endpoints, we calculate this value, and then we just minimize this value over and over again over all the edges. So in this way we are bound to find the shortest path, because let's just assume that 5 and 7 are the 5 and 7 is the best pair. In that case, definitely the shortest path will have a change of color at a particular edge. So we are just iterating over all possible those edges. So that's why this solution should work, and we only need one Dijkstra to compute all this. So this is definitely a better algorithm than the previous one, where we had to do multiple Dijkstras, like maybe 20 Dijkstras to be on the safe side, but here we are running just one Dijkstra. So the constraints could have been set in this way so that this solution works, but the first approach may not have worked. So that's it for now. Thank you.